Hello, today we're going to be talking about polar coordinates. So first of all, let's just talk about coordinates in general. So if I hit the point -3, 3 root 3, just the regular old point, and I wanted to sort of understand where that would be in the coordinate plane, the -3 and 3 root 3, the x value and the y value, they give me enough information to describe where that point is. So like if I start at the origin, which is right here, I could walk 3 units to the left. That's what that -3x value stands for. And then 3 root 3 units up, and I would land on that point in space. Notice that in this two-dimensional coordinate system, I need both an x and a y value in order to determine the exact coordinate. If I just had the x value of -3, well, there's an infinite number of points all lying on this vertical line here that have an x value of -3. Similarly, there's an infinite number of points lying on this horizontal line right here with y values of 3 root 3. So when you combine that x value and y value together, that sort of narrows this down to be one singular point in space. So we can think of this system of giving an x value and a y value. It's a way to describe where a point is in the coordinate plane relative to whatever we're calling the origin, wherever we have fixed our origin. But there are other ways that we could describe where that point is in space. So and that's what we're going to talk about today with polar coordinates, that instead of giving an x value and a y value to describe points in space, we could give an angle and a distance from the points to the origin, and we could describe points that way. So notice when I think of this coordinate plane, and I want to sort of organize my thoughts, usually we have horizontal and vertical sort of grid lines. The grid lines are not present here in this grid, I'm sorry. But those are sort of what allow us to sort of organize all of the points and sort of describe where they are. Notice what I've done here. I have concentric circles that are centered at the origin, and each one, the radius is 1 unit more than the previous. And then I've also marked off all of these angles in standard position, and that could allow me to describe where a point is. So this point in particular, I could describe this point. It is, I believe, 6 units away from the origin. So I could sort of go out 6 units from the origin, and then I would need to figure out sort of what the angle is for this point in standard position. So if I sort of imagine my right triangle here, the angle in standard position associated with that point is, just draw these axes in, if I measured from the x-axis around right there. And I believe, I think I picked this to be a 30, 60, 90 right triangle, that the angle in standard position is going to be 120 degrees. So if I went 6 units out from the origin and then spun around 120 degrees right there, that location right there on the coordinate plane, that's the same location as the -3, 3 root 3. But notice I could describe that point as how far the point is from the origin, which we are going to denote as our r value, and then what the angle is in standard position, which is 120 degrees. Notice I need 2 pieces of information to pin down where that point is. So we're going to sort of flesh out this idea, sort of describing locations in the plane using angles in standard position and the distance to the origin. Obviously this ties all right in with the trigonometry that we have been studying this year. So how would we plot this point? So here we've got a point, and this is written in polar. So points in polar are usually written as r, theta. So for this point here, the radius value is -6, and the angle in standard position is 5 pi over 3. So, we're pretty in tuned, if I just pop back to this other slide for a second, with like when an x value is negative, if I'm plotting this point in, if I'm the Cartesian way of plotting this point, when the x value is -3, like that's pretty ingrained in our sort of our psyche. We're just going to go left 3 units from the origin. But I need to be a little bit careful if I'm calling this radius value negative, because again, it's not the length of the hypotenuse of the corresponding triangle I'm going to draw. That's not negative. It's just that this is directionally negative. So let's see what this means. So if we went to 5 pi over 3, what is that? 300 degrees. That'd be right out here. So if I wanted to look at this point, 6 comma 5 pi over 3. Okay, that would be go out 300 degrees, and then count 6 units from the origin. So that would be the point 6 5 pi over 3. But I want the point -6 5 pi over 3. So negative means I'm going to trace my point back to the origin and then just keep going right on the other side of the origin to right, I believe that's 6 units out. 1, 2, 3, 4, 5, 6. Oh no, that was 7 units out. So let me erase that real fast. So look what's going on here. So the negative radius value. So here's my point 6 positive 5 pi over 3. So if the radius is negative, I'm going to just sort of extend this segment through the origin, keep going on the other side, plot the point. Right there. Now notice I'm thinking of this as moving by my angle first, like I'm finding that ray that corresponds with a 300-degree angle or a 5 pi over 3 radian angle. And then instead of counting 6 units out in the positive direction, towards that 300, I'm just going to count in the negative direction, which is going to be out towards 120. So I'm thinking of the angle happening first. But similar to Cartesian points, if I was plotting a point x comma y, you can think of the y value first. So just to hop back to this other screen, like if I wanted to plot this point, I could have gone 3√3 units up and then 3 units to the left. I'd still wind up at the same point as if I went 3 units left and 3√3 up from the origin. So same thing applies in polar. I could think of, what if I wanted to go 6 units out in the negative direction first? Well, I could do that. I could count out 1, 2, 3, 4, 5, 6 units out on the negative x-axis. Put me right there. And then from that point, I could rotate around 300 degrees. And then where would I land? I would land right there at that point. So there's a couple of ways to conceptualize this, and it's all pretty tough. It's going to take a lot of practice. So let's talk about some basic theory. So the basic theory behind this is a picture that I may or may not have drawn a couple of times this year. That if I pick some point, so x, y, that's the Cartesian way of labeling that point. And then I think about sort of the trigonometry behind that point, is I could make my triangle here perpendicular to the x-axis. I could label that triangle, the right triangle with side lengths x, y, and I'll call that r, and there's theta. So then we can see here that if I wanted to describe that point, I could use the x and the y, or I could use what that angle is and the distance from that point to the origin, which I'm calling here r. So that's sort of the basic theory here. Now there's some nice math that connects all of these values together that we know about. So I mean, what sort of equations can I write using this picture? So the most famous one is x squared plus y squared equals r squared. That sort of connects together the x and y value of a point with, the distance that the point is to the origin. That's great. And then we could write all sorts of trig equations here. So we know that the cosine of theta is x over r, which means that r times the cosine of theta equals the x value. And then by similar logic, r times the sine of theta will equal the y value. So these are all equations sort of that relate thinking about space in a polar manner versus a Cartesian manner. And we're sort of going to use some of this interplay as we want to represent things that we've traditionally represented in a Cartesian manner, and we want to start representing them in polar. So here's a good example. Take this equation, y equals 2x minus 1. It's a line in slope-intercept form. I want to write the equation of that line in polar. So it means that I want to write an equation r equals instead of y equals. So I want to write this sort of I want to write r in terms of theta. That's what I'm thinking of in polar. I want r in terms of theta. Okay, so I'm just going to make some substitutions. So I mean, what do I know that y is? I know y is r sine theta. And I know that x is r cosine theta. Now I just want to take this equation and sort of solve for r. So I'm going to collect everything that has an r on the left-hand side here. So I'm going to subtract 2r cosine theta from both sides of the equation. Factor out an r. And then divide both sides of the equation by sine theta minus 2 cos theta. So look at that. So that right there, that equation, that's the equation of a line in polar. So that's basically saying, like, if you gave me an angle, you could then, like, say, oh, pi over 4. You could substitute pi over 4 in for theta, and then figure out a radius, and then that would say, like, if you went to a standard position angle of pi over 4, and then went out that r value, you would get a point that is on the line. And then you'll start to see things like we're very familiar with the Cartesian form. Like, we can look at that equation and we know all sorts of things, like what the slope of the equation is and the y-intercept, and we can start to generate a table in our heads and stuff like that. We're very familiar with it. I mean, this polar stuff is very new. I mean, it's new to you as of 10 minutes ago. So, you know, it's going to take time to be able to look at an equation like this and know that it's a line and know what the slope is and what the y-intercept is and sort of pick out all those properties. It's tough because it's sort of everything looks a little bit different. So what if we wanted to play this game in reverse? Like, what if we had an equation in polar and we wanted to write that equation in rectangular form? So that means I want y in terms of x. Or I want y as a function of x. I mean, maybe if this winds up being something like a conic section or something, I might not be able to get y in terms of x. Like, maybe I'll wind up with something like the equation of the unit circle, or some hyperbola or something. But I mean, if it's a function, I'll try to write this y in terms of x. So again, I'm going to think back to my sort of basic theory and look for some substitutions to make. So I mean, the easiest one is, I see this r, but I mean, I know what r squared is. R squared is x squared plus y squared. So, I mean, what if I took this equation, multiplied both sides by r to give me an r squared? Gives me something to work with here. So I know r squared is x squared plus y squared. And, oh, look at this, 3r sine theta, but r sine theta is y. Boom, look at that. So I've got the equation x squared plus y squared equals 3y. So I'm already seeing right there, I'm actually not going to be able to write y in terms of x here. I'm going to erase that, because the equation I'm left with is a circle. So I'm not going to be able to write this as a function. I mean, it's not a function. This is a circle. So I mean, let's see, what could we do here? Let's subtract 3y from both sides. Get this equal to 0. Then I could complete the square here. So what do I need to add to both sides here? 9/4 maybe, something like that. And then sort of factor this nonsense. So this will be y minus 3/2 squared equals 9/4. So what is this? So this is a circle. Where's the center? The center is at 0, 3/2, and the radius is 3/2. Nice. So right there, so there's the Cartesian or rectangular form of this polar equation. So again, when you were looking at r equals 3 sine theta, does that look like a circle to us? Probably not, because we need to develop all this intuition in polar by doing lots of examples and working through lots of problems. So we look at this, and it's like, well, we know what the sine curve looks like in Cartesian, but like in polar, that's a circle. That's probably mystical to us right now. Again, you look at the Cartesian or the rectangular equation, it very much looks like a circle. We can identify the center and the radius. So this is just going to take a lot of time and a lot of practice. But I know we're up to the task.